Right, that one is the absolute function from 0 to 2, absolute of 2x minus 1. Right, so what we can consider, right, 2x minus 1 has a x-intercept at 1/2. So absolute of 2x minus 1 is negative of 2x minus 1 for x is less than 1/2. Or we could solve for 2x minus 1, right, to see 2x minus 1 greater than 0 when x is bigger than 1/2, 2x minus 1 is less than 0 when x is less than 1/2. Right, so for the inside to be negative part, we have a negative part of the antiderivative. And the antiderivative is positive for x is bigger than 1/2, equal whichever it is, doesn't matter. Right, so that is the type of the function. So actually, the absolute function is a piecewise function when our interval covers the breaking piece, the breaking point, even though it's not breaking, but that's kind of over here. We take from 0 to 2 of the piece of the absolute function. We will have two different equations applied. From 0 to 1 and from 0 to 1/2, from 1/2 to 2, that's totally two different pieces of function we need to be care of. Right? In the view of the function we have, from 0 to 1/2, we have the function of negative 2x minus 1, or negative 2x plus 1. And from 1/2 to 2, we have 2x minus 1. Right? In the view of triangle, we know already what the area is. I hope you could see. And let's just see what that will be. Each piece itself now have to be a positive number, basically. So from 0 to 1/2 anyway, we have the function that's negative 2x to the 1 plus 1 over 2. To x squared over 2 minus x. Well, we just apply the power rule, which if you're familiar with it, right, the derivative of x squared will give us 2x. Right, so that we see, well, is the x squared. Negative x squared from 0 to 1/2, x from 0 to 1/2, plus x squared from 1/2 to 2, x from 1/2 to 2. I still recommend it to be separate. So what we're going to have is negative of 1/2 squared minus 0 squared plus 1/2 minus 0. That's the first piece. Right, negative sign of 1/2 squared minus the square of 0. The coefficient, always keep it outside of the calculation. That's the key. But otherwise, it will be more tricky. Right? Then the x squared has the term that 2 squared minus square of 1/2 minus 2 minus 1/2. So what we will get from here, from the left, that's 1/4. Minus 0 is still 1/4, the negative sign out of it. That's negative 1/4 plus 1/2. And this one, 2 squared is 4, 4 minus 1/2. Minus the other part is 2 minus 1/2. A force, actually. Right. what we get negative 1/4 plus a half, that's 1/4. Which we get from here is 4 minus 2 plus 1/4. Well, 1/4 plus 1/4 is 1/2. That is 5/2. Right, 2.5 basically. Right, so that is the idea how to do this type of antiderivative. And of course, this thing is tricky enough. The tricky part is we have two pieces of functions to do. Right, that makes it really hard. Maybe when we're doing a curve of function, which absolute of a parabola, we will have three pieces to do. That thing actually is a little harder, right? So, but that type is the hardest part of the type of this kind of questions. We will see. Right, so-called they are the antiderivatives, which, if you remember, right, the antiderivative is used to find the area. Right, the antiderivative is used to find the area. And the next, which is the middle section, is the idea called the Riemann sum. It's kind of the way to illustrate the integration to see what's that actually, how. I use the limit definition to see what's that integral related to the area. Basic simulation formula. So summation, no simulation. Summation formulas. We have the notation, right? The summation of constant for I taking value from 1 to n. We don't see I, but just simply means we're adding n I times. We're adding the c n times. Right, that's c plus c plus c plus the c, that's n times. Basically, right? That's what it means. And intuitively, of course, the multiplication is from the addition, right? If we add the c n times, that means c times n, right, basically. So the summation of constant for I from 1 to n equals c times n. Right, this is a sigma, which is a capital sigma if you have seen that, right? If maybe in statistics, right, that's the capital sigma stands for summation. Right, and the sum for I. Our sum of I, that is n times n plus 1 over 2. Right, for instance, right, if we have a constant in front of the I, it could be taken out of the summation symbol, so it will be c of I, right? Doesn't matter. We only is the only thing concerning is of the variable, right, of the I. Nothing else that coefficient will be concerned, unless it's a constant. A constant will be n times, but if that is coefficient of a variable I, then we have taken the summation, summing the I from 1 to n. That means for the I to be 1 plus 2 plus 3 plus all the way to n, which is the basic arithmetic sequence. 1 plus 2 plus 3 all the way to n. And then the sum of I squared 2n plus 1 over 6. N plus 1, 2n plus 1 over 6. Right, that is the sum of I squared. And sum of I to the third for I from 1 to the n. That is n squared, n plus 1 squared over 4. Right? So that is the formulas we need to, not necessary to remember. You go to your integrational calculus later semester, you will see those things again, hopefully. Right. Then here again, it's just the introduction course. We just give you the idea how do we view the integral. Right, the Riemann sum idea is the right sum is used in different subintervals. Right, we have seen that from A to B we cut into different intervals, the subinterval, that each part has an equal length, and we take is the right endpoints to evaluate. Of course, not necessarily to be equidistant. Right, it is equidistant is only because it will be very easy to, relatively easier to evaluate the result. Right? And of course, when it's n subinterval, which each interval with the length called delta x equals b minus a over n. Right, so we have on our picture the first subinterval, the second, the third, the fourth, the fifth, the sixth subinterval. Right, the first, the second, the third, and of course at the end, the nth. Right? Different subinterval, which each one has the length is delta x equal b minus a over n. Right. Then for I, for the ith subinterval, the right endpoint, this point, right, this ith right endpoint, the xi equals a plus delta x times I. Right, so delta x is the length of the interval. Right, the first will be a plus it for one time. The second right endpoint will be twice of the delta x. The third endpoint will be 3 times of the delta x, the total length more than the a. Right, the ith right endpoint will be I times of the delta x of the small interval, subinterval, more than the a. Right, so that's a plus delta x times I. What the idea is, while we use the right endpoints, we're able to build the right rectangles. We see that while we're able to build the rectangles, from the right endpoints, which we can see is we can approach the area of the rectangle into the area under the curve. Of course, there are small pieces above, some small pieces up below, but that's an approximation, right? So we need to find the area of the rectangle. Basically, the ith rectangle here is the base times height. Right, the base is delta x, and the height is the y value of the right endpoint, which we have the right endpoint already, that's f of xi. But if we want to extend it more, that's a plus b minus a over n times I. That is b minus a over n times f of a plus b minus a over n times I. Right, but it's not necessary because we will illustrate it step by step, or find it step by step, so we will find it at the end anyway. So the total from the first right hand point all the way to the nth right hand point, that is summing everything together from the first subinterval to the nth subinterval of our delta x times f of, or better way to write, f of xi times delta x. Right, that is the Riemann sum, or called the right Riemann sum. But one thing, if we recall what's the idea from pre-calculus, I mean not from differential calculus, that we have finite and different intervals. What about we're cutting more? Well, we're cutting more and more subintervals we get. For more subinterval we get, we will get more rectangles. That means the subinterval is getting smaller, smaller, and smaller by increase the number of subintervals. Right? And the answer of the right sum will be more accurate. Right? The answer, the rectangle will be smaller, the value of the residuals, the errors, right? The errors is the difference between the true area and the approximating area. the errors are getting smaller because the intervals are so close that will the difference between the rectangle y value and the left point of the subinterval, which causing the error, will be getting smaller and smaller, right? So the error piece is getting smaller. So as n goes to infinity, this summation rectangles will yield to the actual integral. Right? That is what we're doing for the Riemann sum. Right, so that is one way to use the Riemann sum to find the area under the curve, or in other words, use the Riemann sum to approach our definite integral. Right, so that is one important idea. Right, basically the Riemann sum is an important idea. Right, you will see later on about the volume, about the area, which refers to surface area, and about the arc length. Right, if you are gonna take the integrational calculus, the application of definite integral, you will see a lot of that. It's based on the idea of cutting into pieces, right, into tiny pieces. So the key thing still is to find the couple of things, right? The delta x and the xi. So find the area of region bounded by the graph of f of x equal x squared, and the x-axis between x equals 0 and x equal 2. Well, we know that this one just refers to the integral from 0 to 2 x squared, that is x to the third over 3 from 0 to 2, that is 8 over 3, supposedly. But using Riemann sum. But we need to use the Riemann sum. So for Riemann sum, we get the picture, right, from 0 to 2 anyway, of the f of x. Right, we have our a equals 0, b equal 2, therefore our delta x is 2 minus 0 over n. Right, that's the first thing to find. And we're cutting n times, right? For this n subinterval, that xi will be a plus delta x times I. That is 0 plus 2 over n times I. Right, so the area is the summation of I from 1 to n of f of xi times delta x. F of xi, that's the 2 over n times I squared. Since f of x is square of x, right? F of xi will be 2 over n times I squared. If I did one more step, that's f of 2i over n times 2 over n. 2 over n I squared, which is the summation of I from 1 to n of 4 over n squared times 2 over n. 8 over n cubed. And the summation is of the I only, so that is 8 over n cubed sum of I squared. And the sum of I squared is n times n plus 1 to n plus 1 over 6. That one is 3n squared, 4 n plus 1 to n plus 1. Right, if you can see the leading coefficient already, you are able to take a limit. Right, the summation is that. And the area, that is the limit as n goes to infinity of the summation, that is taking the infinity as this term. We can expand that out. That is 2n squared, that's 8n squared. 2n plus, that's 3n times 4, that's 12n. 4. And from the knowledge of precalculus, right, this thing has to be 8 over 3. If you divide by n squared of everything, you will see same thing, right? n goes to infinity. 8 plus 12 over n plus 4 over n squared, 3. Right, just divide by n squared for each term. That we get 0, 0 everywhere. That is 8 over 3 at the end. So it pretty much agrees what we have seen in the view of integral. Right, so that's full step. Define a and b. Find out delta x and xi, use the formula to figure out the summation, and finally the area will be the limit as n approaches to infinity of the sum. If you want to give this as a letter s, or to be the sum, right? That will be the limit of the sum. Let's see a function of 4 minus x squared. Between 1 and 2. Let's see. Right, so we have the function of 4 minus x squared from 1 to 2. That somehow is this thing. From 1 to 2 of this graph. Anyway, the a is 1, b is 2, delta x is b minus a over n. That is 2 minus 1 over n is 1 over n. Xi is a plus delta x times I. That is 1 plus 1 over n times I. Which is 1 plus I over n. But then the sum, that is summation from 1 to n, f of xi times delta x. Right, nothing else but just the area of the rectangle, right, the base times height. So we didn't take nothing, so f of xi, that's 4 minus the square of 1 plus I over n times 1 over n. That's 4 minus 1 minus 2I over n minus I square over n squared. Right, the perfect square formula is squared plus 2ab plus b squared. And we take difference, that's 3 minus 2I over n minus I square over n squared, which is sum of 3 over n, sum of 2 over n squared, sum of I square over n to the third. Right, that is sum of 3 over n minus 2 over n squared times sum of I minus 1 over n to the third times sum of I squared. What we get is apply the formula, right? 3n minus times n, 2 over n squared, the summation of I is n plus 1 over 2. That's 3 here. n plus 1, 2n plus 1 over 6. Minus n plus 1 over n minus n plus 1 2n plus 1 over 6n squared. Right, that is the sum. Well, we have separated into 3 parts of the product by 2 over n squared times I and n cubed on the denominator, 1 over n cubed times I squared. Then we get multiplication of the sum, right? 3 over n times n, 2 over n squared times the summation of I, and 1 over n to the third times summation of I squared. We have everything cancelled, 2, 2, and so on. Right? So we get the area equal the limit as n approaches to infinity of the sum. That is infinity of the 3 minus n plus n1 over n minus n squared plus 3n plus 1 over 6n squared. Right, so we could divide it separately. Limit n approaches to infinity, 3 minus 1 plus 1 over n minus 1/3 plus 1 over 2n plus 1 over 6n squared. Right, just divide each term into it. Right, divide the n, that's 1 plus 1 over n, divide by n squared, we get 2 over 6, which is 1/3. That we get 1 over 2n, the last one we have 1 over 6n squared. As n goes to infinity, we get 3 minus 1 plus 0 minus 1/3 3 minus 1 is 2 minus 1/3, which is 5 over 3. Right? If we see in the view of integral, right, we get from 0 to from 1 to 2, 4 minus x squared. That is 4x x to the third over 3, 4 times 1 minus 8 minus y 7 over 3. It's supposed to be 5 over 3 in the view of the integral. Right, so this summation agrees with the integral as the result. Right, but what we're asked to do is to use the Riemann sum to find the area. So that is the entire full step of what we're supposed to do. Most part is just the algebra, and the setting up is actually the most tricky part. Right. So, for our course, right, what we have seen to wrap up, right, the first thing before our differentiate was the limit. Right, and after the limit, we have seen the properties or the rules of differentiation, like a lot of them, right? The exponential logarithmic function, the power rule, product quotient chain rule, right? The different thing. And the trigonometric functions and inverse trigonometric functions. And for the introduction of the integration, we just see the power rule and the integration of constant and of course the linear combinations. We have seen a little bit about the Riemann sum, which is the right sum, right? Of course, you could have different way to summation it. Maybe left sum, maybe something could use the rule of trapezoid, right? That's also appropriate. It's not like using the rectangle, but using the trapezoid to find the area of trapezoid and summation, sum that trapezoid and take limit. The Riemann sum, the rule using just the right hand points of the rectangle is just the right sum. Right, and of course if you go to if you're taking the integrational calculus, that will be much harder than our course here, right? That is just the Riemann sum. And for every differentiate formulas, right, we will have an integration formula corresponding to it. And that will be much harder. Right? You need to distinguish what to do basically for the given functions. Right, so anyhow, that is everything for our chapter here, for our material here. Thanks for watching and take care.